We have stood on the moon. We have driven rovers across the red dirt of Mars. We have even dropped submarines into the deepest scar on the ocean floor, 7 miles down in the Mariana Trench. But there is one entire ocean on our own planet that we have barely touched. It circles the bottom of the Earth, and it is, without exaggeration, the single hardest place on this planet to reach. In most oceans, the danger is waiting for you at the bottom. Here, the danger starts before your equipment even touches the water. So what is actually blocking us? And after decades of trying, what have we found in the handful of moments we've managed to sneak a look inside? The easy assumption is that this is just an ice problem, the same kind of problem we already solved in the north. Up at the Arctic, when the sea freezes over for winter, we send in icebreakers, ships built to ride up onto the frozen surface and crush it under their own weight. It works. So why not just do the same thing down south, punch a hole, and lower a submarine through? Because what's blocking the Southern Ocean isn't frozen seawater. It's a shelf of glacial ice. A slab of compacted snow that built up on the continent over hundreds of thousands of years and has since slid off the land and is now floating on the water, in places over half a mile thick. That's not an obstacle you break. Sailing an icebreaker at an ice shelf is closer to driving a sedan into a mountainside and expecting the mountain to move. Because these shelves stretch for hundreds of miles off the actual coastline, enormous stretches of the Southern Ocean sit permanently sealed under a ceiling of solid ice. Say you do find a crack at the shelf's edge, a gap just wide enough to lower a camera through. Congratulations, you've made it past step 1. Step 2 is where things really start to fall apart. Water that kills machines. The water trapped beneath an Antarctic ice shelf is what oceanographers call supercooled. Ordinary seawater freezes around 28 to 32 degrees Fahrenheit depending on salinity. But under the crushing pressure of the shelf above it, this water can drop below its own freezing point and still stay liquid. For a machine, that is a nightmare environment. Cold, this extreme attacks equipment on almost every level at once. Battery chemistry slows down so severely that a power cell rated for half a day of operation can be dead in under an hour. Hydraulic fluid, the stuff that lets a robotic arm bend and grip, thickens into something closer to cold honey, so the arm simply stops responding. And the metal itself turns brittle. Steel and titanium that could normally take thousands of pounds of force can shear clean off after one hard knock against a rock. Send a multi-million-dollar robot down here, and the ocean can turn it into scrap in a single dive. Now imagine a person down there instead of a robot. Even in a top-tier dry suit, supercooled water pulls heat out of the human body roughly 25 times faster than freezing air would. The body responds by yanking blood away from the hands and feet to protect the organs. Within minutes, a diver can lose the fine motor control needed to even operate their own gear. And the cold isn't the only threat. Look up under an ice shelf, and there's no flat ceiling. It's an inverted landscape of frozen spikes and jagged canyons with zero air pockets, because it's glacial ice, not frozen seawater. Lose the guideline back to your entry hole in a place like that, and there is no swimming to the surface. The surface, for all practical purposes, doesn't exist. Why even submarines stay away? Surely, though, a nuclear-powered military submarine could handle this. Submarines are built to operate deep, in the dark, for months at a time. You'd think the unmapped water under Antarctica's ice would be exactly the kind of place they're designed for. It isn't. Submarines navigate primarily with sonar, sending out a pulse of sound and reading the echo to build a picture of what's around them. In open water, that works beautifully. Under a shattered, jagged ice ceiling, it falls apart. The sound doesn't return a clean echo. It bounces between ice spikes and canyon walls and comes back scrambled, creating false readings that can hide a genuine hazard while flagging open water as a wall. Worse, the ice shelf is not a static structure. It groans and shifts constantly, and chunks the size of city blocks can calve off and sink without warning. A channel that was clear an hour ago can be sealed shut the next. And if a submarine ever did get trapped under a mile of solid ice, there is no rescue operation that reaches it. No radio signal gets through, and there's no way to blast a path out. It would simply be gone. The underwater ice tornado. Even a machine engineered to survive the cold and navigate the maze still has to contend with something the Southern Ocean does almost nowhere else on Earth: the Brinicle. When surface seawater freezes into sea ice, the water molecules lock into a crystal structure, but the salt gets pushed out and left behind, forming pockets of extremely salty, extremely dense brine. Because this brine is both far saltier and far colder than the water around it, it sinks, and everywhere it touches on the way down, it flash freezes the surrounding seawater into a hollow tube of ice. The result looks exactly like a slow-motion underwater tornado, growing downward toward the seafloor. When it finally reaches the bottom, the brine keeps spreading, crawling across the seafloor and freezing slower-moving animals, starfish, urchins, small fish, in place. If a small submersible gets caught in a Brinicle as it's forming, the same supercooled brine can freeze its thrusters solid before the pilot even realizes what's happening. 6 months of absolute darkness. On top of all of that, exploration here runs on a brutal clock. For a short window during the Antarctic summer, the sun barely sets, temperatures become almost survivable, and enough of the surrounding sea ice melts back for research vessels to approach. When winter arrives, that window slams shut. The sun disappears for months at a time. Temperatures can fall toward minus 100 degrees Fahrenheit, and the sea ice expands so fast it roughly doubles the physical footprint of the continent. A ship that misjudges its exit and lingers too long can find seawater freezing solid around its hull, with the surrounding pressure slowly crushing the metal. Every research vessel in the region clears out well before that happens. For half the year, this ocean is simply closed. The ecosystem that shouldn't exist. Given everything working against life down here, you'd expect the water under the ice shelves to be as barren as the ice above it. The interior of the continent itself is close to lifeless. No plants, no land mammals, almost nothing beyond a few microbes, and the penguins clustered along the coast. The ocean underneath tells a completely different story. It's home to fields of coral, forests of sponges, the lake sealed since before humans, and a long list of highly specialized predators that spend their entire lives in sub-zero water. The reason comes down to oxygen. Cold water holds dramatically more dissolved oxygen than warm water, and that surplus has let evolution take some strange turns. Combine high oxygen with an extremely slow, cold-adapted metabolism, and you get polar gigantism. A sea spider on a tropical reef might be the size of a fingernail. Off Antarctica, the same basic animal can have a leg span over 2 feet across, creeping along the seafloor on stilt-like legs to feed. And then there's the animal that defines this entire ocean, the colossal squid. A specimen caught in the Ross Sea weighed close to 1,000 pounds, armed with rotating hooks along its tentacles. Its eyes measure roughly 11 inches across, about the size of a dinner plate. The largest eyes ever recorded in the animal kingdom, built to catch the faintest flicker of bioluminescent light or the shadow of an approaching sperm whale, These are only the animals that occasionally drift out to the edges of the ice, where cameras or predators can find them. What lives hundreds of miles in, underneath the thickest, most permanent parts of the shelf, is almost entirely unknown. And bringing these animals to the surface to study them doesn't really work either. Their proteins and cell structures are built to function at a precise, near-freezing temperature. Haul one up into water that feels freezing to us, but is warm by their standards, and their metabolism spikes faster than their gills can supply oxygen for. Their specialized cold water proteins start to unfold. In the most literal sense, they begin to come apart at the molecular level. We can't survive down there, and they can't survive up here. The lake sealed since before humans existed. The water trapped under the floating ice shelves is actually the more reachable part of this story. Buried in the middle of the continent, under roughly 2.5 miles of solid ice, sits an entirely separate hidden world, a network of subglacial lakes and rivers that ground-penetrating radar revealed decades ago. The largest of them is Lake Vostok, a body of fresh water, roughly comparable in size to Lake Ontario, kept liquid by geothermal heat from below and the immense pressure of the ice above. Estimates put its isolation at somewhere between 15 and 25 million years, cut off from sunlight and the atmosphere the entire time. For 2 decades, Russian researchers drilled toward it, stopping the core dozens of meters short of the water each season specifically to avoid contaminating a lake that old. In February 2012, after 22 years of work, the drill finally broke through. Lake water surged up the borehole and froze on contact with the frigid air, and the team pulled the ice sample back the following season. But breaking through didn't come free. Some of the antifreeze and drilling fluid used to keep the borehole open did mix with lake water at that boundary, exactly the kind of contamination scientists had spent 20 years trying to prevent. It's still debated how much that compromised the sample, and full-scale exploration of the open lake, sending a camera or probe into the water itself, hasn't happened, largely because introducing modern surface bacteria into an ecosystem isolated for millions of years could wipe out whatever lives there before we ever get a clear look at it. In other words, we've technically touched the edge of a 15-million-year-old time capsule. We still haven't dared to actually look inside it. A map that erases itself. Even the small fraction we have managed to explore doesn't stay explored. Scientists have lowered narrow pencil cameras through boreholes and spotted amphipods and ice worms drifting in the dark. But a 6-inch patch of water viewed through a borehole for a few hours isn't a survey. It's closer to judging an entire stadium by peering through the front door's keyhole. And unlike the Mariana Trench, where the rock walls stay put for centuries, the Southern Ocean's coastline is made of moving ice. The shelves creep forward constantly, fed by the glaciers behind them, until the pressure becomes too much, and enormous sections calve away as icebergs the size of small countries. A channel a robotic sub navigated safely in 1 decade can be crushed shut or relocated miles away by the next. There is no such thing as a permanent map of this place, only a temporary snapshot of a landscape actively erasing itself. The paradox of finally getting in. There is really only one scenario in which this ocean becomes easy to explore. The ice shelves have to disappear, and as global temperatures climb, that process is already underway. Shelves are thinning, fracturing and collapsing at a pace that would eventually open this water to ordinary ships and submarines. But warmer water holds less dissolved oxygen, and the entire ecosystem down there, the sea spiders, the colossal squids, every animal running on that slow, cold-adapted metabolism, depends on that oxygen surplus to survive. Melt the barrier, and the water that made this ecosystem possible in the first place stops existing along with it. The very thing that would finally let us see this place clearly is the same thing that could leave nothing left to see. So maybe there's something fitting about the fact that the most guarded ocean on Earth stays exactly that. Guarded. Whatever is still drifting in the dark beneath that ice has had the place to itself for longer than we've existed as a species. If this pulled you in, hit subscribe so you don't miss what we dive into next, and drop a comment telling us which mystery of the deep we should uncover after this one. I read every single one of them. Thanks for watching Lucent Nocturne. We'll see you in the dark.